Hello, I'm Norman Wildberger, and today we're going to talk about 2x2 matrices and their applications. A 2x2 matrix, like this one, is an array of numbers, 4 altogether, in a square with little round brackets. And we have two kinds of notation that we use for the entries of the matrix. We could either use indices, A sub 1, 1, A 1, 2, A 2, 1, A 2, 2, or a more direct notation, just A, B, C, D. Both have advantages and disadvantages. If we have a lot of different matrices, then it's probably better to use this kind of notation because it keeps things straight. If there's only one or two matrices involved, then this kind of notation is perhaps preferable because it's just simpler. 2x2 matrices have various operations defined on them. And the two simplest operations are scalar multiplication and addition. So we define scalar multiplication in the following way. Lambda is a scalar or a number, like 5 or -3 or 4/5. And we define lambda times this matrix to be what we get when we multiply each of the entries by lambda. And if we have two matrices, then we define the sum of the two matrices to be what we get when we add the entries in each component. A plus E, B plus F, C plus G, and D plus H. In fact, with these two operations, we don't actually need to define subtraction separately, because subtraction can be thought of as adding a matrix plus -1 times the other matrix. So subtraction is included in these. These are the two fundamental basic operations. If this was all there was, then matrix arithmetic would not be all that interesting. But what makes it more interesting is that there's another much more subtle operation called matrix multiplication. So let's review how you multiply two matrices. The matrix A, B, C, D times the matrix E, F, G, H is another 2x2 matrix. And the first column of that matrix is obtained by multiplying this matrix by this first column here. And that means AE plus BG and CE plus DG. The second column of the product is obtained by taking this matrix and multiplying it by the second column, and that means AF plus BH and CF plus DH. That's the matrix multiplication. Now, the way I want you to think about 2x2 matrices is that it's an arena for doing arithmetic, but it's a more elaborate or more sophisticated kind of arithmetic than we're used to. And to make that clear, I want to introduce a simpler version of matrices, the idea of a 1x1 matrix and the idea of arithmetic with 1x1 matrices. This is a subject that's usually not mentioned very explicitly in most linear algebra texts because it's so simple. But I think it provides a really good bridging to go from the 1x1 to the 2x2 and then the 3x3 and so on. A 1x1 matrix is almost the same thing as a number, but not quite. So here is a 1x1 matrix. It consists of a number, A, so A is a number, enclosed in round brackets. The round brackets means that it's not quite a number. But we can see that 1x1 matrices are essentially numbers, except for the brackets. It's really not much different. And here are the three operations for 1x1 matrices. We can multiply a 1x1 matrix by a scalar, in other words, by a number, just by multiplying the entry by that number. We can add two 1x1 matrices just by adding the entries. And we can multiply two 1x1 matrices by multiplying the entries. Now let me say just very briefly, what kind of numbers are we thinking about here? Well, the simplest framework for doing linear algebra is when we think of numbers as being rational numbers. Things like 3/4 or 5 or -4/9. Fractions or negatives of fractions. Later on, we're also going to need more sophisticated numbers, involving square roots or more elaborate constructions. But we don't really need the full complexity of the real number system when we start linear algebra. So for most of our initial talks, when I talk about a number, I'm usually thinking of a rational number. Now I want you to think about this following idea, that a 2x2 matrix is a lot like a generalized number. It generalizes the idea of a one-by-one matrix and introduces a richer and more elaborate kind of arithmetic. But still, there's a very close connection between these two things, and it's that connection that I want you to keep in mind. When we learn to do arithmetic in public school, it's very valuable for us to have a very clear idea of what the rules or the laws are that govern this arithmetic. And here I've listed the main laws for arithmetic with one-by-one matrices and also with two-by-two matrices. It turns out that the main laws of arithmetic involving the three operations that we've talked about are essentially the same for one-by-one matrices and for two-by-two matrices, with essentially one major exception. But apart from that one exception, the laws are essentially the same. And let's have a look at those laws. All right, so here is one law, the commutative law for addition for one-by-one matrices. That the matrix A plus B is equal to the matrix B plus the matrix A. Now, I prefer to rewrite this in a slightly more general form by talking about the names of the matrices rather than the matrices themselves. So instead of writing this, I'm going to prefer to write simply A plus B equals B plus A, where I'm thinking of A as representing this matrix and B representing this matrix. When I formulate the laws this way, then there's the possibility of interpreting them in a different way and thinking, well, A and B could be two-by-two matrices. So that's the advantage in this framework, that it actually applies both to the one-by-one case and to the two-by-two case. And in fact to the three-by-three case and higher on, as we'll see later. Okay, so what are the main laws? Well, this law here is the commutative law for addition. This law is the associative law for addition. That if you combine A and B by adding them, A plus B, and then to that you add C, it's the same thing as when you add A to the sum of B and C. There's an associative law for scalar multiplication. If you take a matrix A and you multiply by a number mu, and then multiply that by a number lambda, that's the same as if you started with the matrix A and multiplied by the product of lambda times mu. There are two distributive laws, that lambda plus mu times the matrix A is lambda times A plus mu times A. And if we have lambda times a sum of two matrices, A and B, then that's the same as lambda A plus lambda B. There's a very important associative law for matrix multiplication, that A times B times C is A times B times C. And for the one-by-one matrices, there's the commutative law of multiplication. A times B equals B times A. Now, I've written this in red with some exclamation marks. This law is different from all the other laws on this page because it applies only to the one-by-one case. This is the case that distinguishes one-by-one matrix arithmetic from two-by-two matrix arithmetic. Okay. This is valid for one-by-one matrices, but not valid for two-by-two matrices. So I've put it in red. There are some other distributive laws having to do with matrix multiplication and addition. A times B plus C is the same as A times B plus A times C. And A plus B times C is the same as A times C plus B times C. And then there are a few laws having to do with some special matrices. The special matrices are the zero matrix and the identity matrix. In the one-by-one case, the zero matrix is just the matrix which has a zero in it, and the identity matrix is the matrix that has a 1 in it. And these two matrices have some special properties. First of all, if you multiply an arbitrary matrix A by the number 0, the number 0 is a little bit elongated to distinguish it from this round matrix 0. So the number 0 times the matrix A is the zero matrix. And the number 1 times the matrix A is the matrix A. The identity matrix has the property that if you multiply it by any matrix in either order, so I times A or A times I, you get A back again. Now these also have analogs for 2 by 2 matrices. I'll tell you about them in a minute. But you have to replace these 1-by-1 matrices, of course, with the corresponding 2-by-2 matrices. But when you do that, the same laws are satisfied. And now we come to the most complicated law, and perhaps the most important one. It's that if delta of A does not equal to 0, then there is another matrix B which has the property that A times B equals B times A equals the identity matrix. So I haven't told you yet what delta of A is, but I think you can guess already that it's a determinant, and that's in fact correct. If the determinant of the matrix A is not equal to 0, then we can invert that matrix. In other words, we can find another matrix that multiplies together with it in either order to give the identity matrix. This is the analog in arithmetic of finding the inverse of a number. So let's have a look at this law in some more detail. So let's have a look at this last very interesting law with this determinant function. First of all, what is the determinant of the matrix A? For the 1-by-1 case, the determinant of the matrix A, here's the matrix A, is the number A. So it just picks out its entry. The determinant of the matrix is a number. For the 2-by-2 case, the determinant of the matrix ABCD is this number that we've seen many times, AD minus BC. That's the definition of what we mean by the determinant. So here is again that inverse law. If the determinant is not equal to 0, then there's a matrix B satisfying AB equals BA equals the identity. Let us prove this. Let's prove and see why this law is valid. First of all, in the 1-by-1 case where things are relatively simple. Suppose A is the matrix with entry A. And here is the determinant of A, it's the number A, and suppose that it's not equal to 0. In that case, let's look at the matrix B, whose entry is 1 over A. Now when you take 1 over something, you have to be careful that the denominator is not 0. So our assumption is just guaranteeing that this makes sense, that that 1 over A is defined. Well, what is A times B? It's the matrix A times the matrix 1 over A. And the way you multiply, you just multiply those numbers, so you're getting the matrix with entry 1. And that's what we call the identity matrix. And if you do it in the other order, it's nothing different. B times A is 1 over A times A. That's still the matrix with entry 1. That's the identity matrix. So it's easy to see that this is the case. That's the inverse matrix to this one. And we need the determinant to be non-zero for that to work. However, in the 2-by-2 case, it's a little bit more subtle. But fortunately, we've already worked this out. Now let's have a look at the 2-by-2 case. First, we need to introduce the matrices O and I. The 0 matrix is just the matrix with all zeros. However, the identity matrix has this particular form, 1, 0, 0, 1. Ones on the diagonal and zeros everywhere else. We have to make sure that that actually satisfies the crucial property of the identity matrix. So if you take the identity matrix and you multiply by any other matrix, what do you get? Let me remind you how you do the matrix multiplication. To find the first column, we take A plus 0 and 0 plus C. To get the second column, we take this times this plus this times this, so that's B plus 0, that's B. And this one is B times 0 plus 1 times D, that's D. So we see what we're getting is just this same matrix back again. The identity matrix really is acting like the number 1 in the matrix multiplication sense. And similarly, you can check that when you multiply it in the other order, you also get the same thing. Alright, so what does the inverse law say? It says that if the matrix A has determinant, which is non-zero, then there is an inverse matrix. And what is that inverse matrix? Well, here it is right here. There's the matrix A, and this is the matrix that's going to be the inverse. And have we seen this before? Yes, we have. This we've already obtained when we looked at this fundamental problem of inverting a change of coordinates. I told you that this was the fundamental problem in linear algebra, and here we see that it's intimately connected with finding the inverse of this matrix in this arithmetic situation. Okay, and what was the formula? We took the entries of the matrix A and we swapped D and A, the diagonal entries, and we subtracted, or we negated the off-diagonal entries, minus B and minus C, and we divided each of them by the determinant. And now let me convince you that the product of this matrix times this matrix really is the identity matrix. Okay, it's a very interesting computation. So how do we compute the first column? We take, first of all, this times this plus this times this. Okay, what are we getting? We're getting AD over delta minus BC over delta. So AD minus BC all over delta. And what's the next entry down here? It's this times this plus this times this. CD over delta minus CD over delta. Well, they cancel out, so we get 0. What about the second column? The second column we get by taking the second column and multiplying it first by the first row. A times minus B over delta plus B times A over delta. They cancel out also, we get 0. And finally down here, minus B times C over delta plus D times A over delta. Well, that's AD minus BC over delta. But when we look at this, the delta is by definition AD minus BC. So these numbers here on the diagonal are just 1. And we do indeed get the identity matrix. And please do it yourself. Check that we take these same two matrices and we multiply them in the opposite order, B times A, that you also get the identity matrix. So we have seen that the inverse always exists if the determinant is non-zero, and we use this notation. B is A to the minus 1, so that means the inverse of A. It's the same notation that we use for numbers to represent the inverse of a number. So our fundamental problem of linear algebra is intimately connected with the most complicated arithmetical operation, which I probably don't need to remind you is division. Addition, subtraction, and multiplication, even for ordinary numbers, is relatively simple, but division is in practice the more complicated one. That's also the situation here with matrices, and finding the inverse or dividing by the matrix A is essentially equivalent to this computation that we've done inverting a change of coordinates. This is the crucial formula for the inverse of the matrix A. Alright, now you have a major exercise in front of you. The exercise is to go back to those laws of arithmetic that I wrote down all on one page and to verify that they are true both for the 1-by-1 matrices case and for the 2-by-2 matrices case. So, let's call it exercise 6.1. Check each of the laws for 1-by-1 matrices, that's relatively easy, and also for the 2-by-2 matrices. And what I want you to do is to write out complete proofs. This is a great place to practice writing out mathematics clearly and precisely. So, I'm going to give you some examples to show you what I mean, what I want you to do. Okay, so let's prove one or two of the laws. And we're going to prove them in the 2-by-2 case, which is a little bit more non-trivial. So here's one of the distributive laws. It's that lambda times A plus B equals lambda A plus lambda B. We want to prove that this law is correct for 2-by-2 matrices. Now let me make an obvious remark. It's not sufficient to say, all right, let's try it for some random matrices A and B and some random scalar lambda. Even if you prove it for a lot of different special cases, you still haven't proven it in general. So we want to have an argument that is general. And to do that, we introduce general matrices and a general scalar. So we start out by saying, let's let A be the matrix A, B, C, D, and B be the matrix E, F, G, H. Period. That makes that a sentence. We try to write sentences starting with capital letters, ending with periods, even when we're writing proofs for mathematics. We try at least. Alright, then what happens? Well, I'm going to compute this left-hand side. So lambda times A plus B. What is it? Well, there's A, there's B. I know how to find the sum. The sum is A plus E, B plus F, C plus G, and D plus H. And now I have to multiply by lambda. I know how to multiply by lambda. I just multiply each of the elements by lambda. So there's lambda times that, lambda times that, lambda times that, and lambda times that. So we've just established this formula. Now we just use the basic distributive law for ordinary numbers inside each one of these entries. Lambda times A plus E These are all three just ordinary numbers. That's the same as lambda A plus lambda E. So we're using the fact that we know the distributive law works for ordinary numbers. Similarly, this, and this expand out to give us those three as well. So now we've reduced the left-hand side pretty well as much as we can. Now let's look at the right-hand side, which is lambda A plus lambda B. Well, what is lambda A? It's what we get by taking the matrix A and multiplying everything by lambda. Lambda B is what we get by taking the matrix B and multiplying everything by lambda. And now we need to add these two. How do we add these two? We just add component-wise. Lambda A plus lambda E, lambda B plus lambda F, and so on. And now we see that this matrix and this matrix are exactly the same. So we can say lambda A plus B equals lambda A plus lambda B. So there's our conclusion written as a sentence. And there's a little square denoting the end of the proof. So that's a model for what I want you to do. I want you to go through all those laws and write down proofs for the 2-by-2 case. And you can also think about the 1-by-1 case, which is relatively simple. Let me give you another example, which is also a very important and non-trivial law. The associative law for matrix multiplication. This is a major result which is non-trivial. It's that A times B, evaluated first, then times C, is the same as taking the matrix A and multiplying it on the right by B times C. So let me go through the proof of that. First of all, let's let A be this matrix, A, B, C, D, B be the matrix E, F, G, H, and C be the matrix I, J, K, L. We'll calculate the left-hand side first. A times B first times C. Well, we have to calculate A times B. What's that? Well, here is exactly A times B. AE plus BG, CE plus DG, and so on. And now we have to multiply that by C. Okay, here's where it gets a little bit involved, because now this matrix is already getting a little bit complicated, but we have to just apply our basic rule for multiplication. How do we multiply this 2-by-2 matrix by this 2-by-2 matrix? Well, we work out the first column first. Meaning, we take first this times I plus this times K. That's the first entry. And below it, this times I plus this times K. The second column obtained by taking the same matrix and multiplying by JL. So this times J plus this times L. And below it, this times J plus this times L. You have to write neatly, write big, write carefully. What about the right-hand side? A times BC. Well, now we're asked to multiply, there's the matrix A, times BC. This is the product of B and C. So we have to go back up here, B and C, and multiply these two matrices. AE plus FK, GI plus HK, the next column. EJ plus FL, and GJ plus HL. Alright, so we've got these two matrices here, that's A times BC, and now we have to multiply them. The first column is obtained by taking this matrix times the first column. A times this plus B times this. And the second entry, C times this plus D times this. The second column obtained by taking this matrix times the second column. A times this plus B times this. I've written it there. And below it, C times this plus D times this. Alright, so there's A times BC, and up here we had AB times C. And now we have to compare these two expressions. And we're going to do that term by term. So let's have a look at the top left entry. This entry here compared to this entry here. Well, they're altogether 4 terms. And they're altogether 4 terms here. Let's see if they agree. So here there's an AEI, and here there's an AEI. Here there's an AFK, and here there's an AFK. A BGI, and a BGI. And a BHK, and a BHK. So the top left entries agree. Let's go over to these entries here. Here we have AEJ, here we have AEJ, AFL, AFL, BGJ, BGJ, and BHL, BHL. These two terms agree. This one here, compared with this one here. CEI, CEI, CFK, CFK, DGI, DGI, and DHK, DHK. And finally, this bottom entry here on the right, CEJ down here and CEJ up here. CFL and CFL, DGJ, DGJ, and DHL, DHL. Our careful bookkeeping has paid off. We can see that these two matrices are exactly the same. So we conclude that AB times C equals A times BC. It's a bit of magic, isn't it? So now we're in a happy position. We have a very good arithmetic with 2x2 matrices. We have laws of arithmetic which are not much different from the laws of 1x1 matrices or ordinary numbers. And now we can apply this arithmetic to the geometry of plane transformations. Ordinary arithmetic with numbers is not rich enough to capture two-dimensional geometry. But this arithmetic with 2x2 matrices is ideally suited for this job, as we'll see. So linear transformations, here we come. The relation between matrix multiplication and two-dimensional geometry comes about when we remember that a matrix can multiply a vector. So here's a matrix and here's a vector. And when we multiply them, this is the definition, we get ax plus by over cx plus dy, we get another vector. So multiplying on the left by this matrix A sends the vector v, say, which is xy, to a new vector v prime, which is x prime y prime. Mathematicians like to talk about functions. This is a function that sends a vector to another vector. And in the plane, we can visualize this very concretely. We can set up a coordinate system. And then we can think of the vector v as being represented or visualized in that coordinate system. We can think of v prime as being some other vector. And we can think of the transformation as physically sending this vector to this vector. This transformation, because it's acting like a function, we can often introduce a kind of a notation for it. We can, let's say, give this transformation a name. Let's call it t. Okay. So then we say that t of the vector v is the vector v prime. Thinking of inputting v and outputting v prime. Now we can use any coordinate system we like, but for the purposes of the rest of this talk, I'm going to use the standard coordinate system, which I've so far resisted doing on purpose. But now let's use the standard coordinate system that you're all familiar from high school, where the axes are really horizontal and vertical, where there's equally spaced numbers 1, 2, 3 in the x direction, equally spaced numbers 1, 2, 3 in the y direction, and there's a definite origin. This still fits into our framework because this is still essentially given by the two basis vectors E1 and E2, just that we haven't drawn all the other grid lines. So we're going to illustrate various matrices and how they act on the vectors in this standard Cartesian coordinate system that's familiar in high school. And that, of course, has many applications. So probably I should start with the identity matrix, but that's a little bit too easy because the identity matrix times any vector is the same vector, so the transformation doesn't move any vector. Let's start instead with something which is almost the identity transformation. It looks like the identity matrix, except that instead of having a 1 down here, there's a -1. So let's have a look at what this matrix does when we multiply it by this vector xy. So here's the algorithm. 1 times x plus 0 times y, that's x. And 0 times x plus -1 times y, that's -y. So multiplying by this matrix sends the vector xy to the vector x minus y. And what does that do geometrically? Well, let's look at some examples. There's the vector 3, 1, 3 in the x direction, 1 in the y direction. So it would be sent to the vector 3 minus 1, which is where? Well, the x component hasn't changed, but the y component is now minus 1. So it's gone from there to there. Another example, here, say this vector here, which has components minus 1 and 2, so that's the vector minus 1, 2 there. That's sent, under this same transformation, to the vector minus 1, minus 2, which is down here. And if you stare at it for a little while, you see that what this transformation is doing is it's reflecting in the x-axis. Because the x component of any vector is unchanged, but the y component is simply going from positive to negative, or from negative to positive. So this is a reflection. And it has the property that if you do it twice, you get back to where you started. So if you apply the same matrix to this vector, then you're going to get back to where you started. If you apply the transformation to this, you're going to go back to there. Here's another example, example number 2, where our matrix is the matrix 0, 1, 1, 0. Let's multiply that by xy. 0 times x plus 1 times y, that's y. And 1 times x plus 0 times y, that's x. So multiplying by this matrix takes the vector xy to the vector yx. What's that do geometrically? Well, the vector 3, 1 gets sent to the vector 1, 3. The vector minus 1, 1 gets sent to the vector 1, minus 1. What this is a reflection in the line y equals x. In the same way that this was a reflection in the line y equals 0, or the x-axis. So this one also has the property that if you do it twice, you get back to where you started. Our next example is a combination of the two previous ones. I'm going to take the matrix 1, 0, 0, minus 1. That was the matrix corresponding to reflection in the x-axis. I'm going to multiply it on the left by the matrix 0, 1, 1, 0, which was the matrix for reflection in the line y equals x. What happens if we multiply these two matrices? Well, we get 0 plus 0, and 1 plus 0, 1. This next column, 0 plus minus 1, and 1, no, that's 0 plus 0, that's another 0. So we get this matrix 0, minus 1, 1, 0. Let's see what it does to the vector xy. 0 plus minus y, x plus 0, we get minus yx. What does this do? There's the vector 3, 1. The vector 3, 1 gets sent to the vector minus 1, 3, which is there. If we do it again this time, we would not get back to where we started. If we did it again to minus 1, 3, we would get, let's think if this was minus 1 and this was 3, we would get minus 3, minus 1, which would be down here. This is a rotation by a half turn, or 90 degrees. What does it do to the vector minus 1, minus 1? It sends it to the vector 1, minus 1, another rotation. Everything is rotated by 90 degrees. And what we've seen here when we computed this matrix by a product of those two matrices is geometrically that this rotation is the product of two reflections. If you first reflect this vector in the x-axis, and then you reflect it in the line y equals x, that's the same as just rotating it by 90 degrees. Let's try it again for this matrix here too. If we take this vector here and we reflect it, we get the vector up there, and then we reflect it in this line y equals x, we get that vector down there. So rotation by 90 degrees is the product or the composite of two reflections. The matrix multiplication corresponds to composing transformations. How important is that? That's very, very important. It means that the geometry of composition of transformations is directly linked to the arithmetic of the 2 by 2 matrices. We've talked so far about 4 interesting matrices. The identity matrix, and then these 3 particular matrices. Let me somewhat arbitrarily, but not entirely arbitrarily, give them some names. Let's call this one G, and this one R, and this one B. Then it's very interesting and pleasant exercise to write out all the possible ways of multiplying 2 of these 4 matrices. The way the identity multiplies with any one is already clear. The identity times r, for example, has to be r because I is the identity. But if we multiply any two of these, we get interesting relations. For example, r times g is b. But g times r is minus b. That's an example of when you multiply matrices in different order, you get different outputs. But sort of symmetrically, b times g is r, and g times b is minus r, and r times b is g, and b times r is minus g. Another thing you can do is multiply a matrix by itself. We write g times g, or just g squared. So we can check that g squared is the identity matrix, r squared is also the identity matrix, but b squared, this one here, which was the 90-degree rotation, its square is minus the identity. Now it turns out that if you take the four matrices together with their negatives, that set of 8 matrices forms a closed group under multiplication. So that means that when you multiply any two of them, you get another element in the set. That's a very pleasant, interesting feature that turns out to be closely related to the geometry or the symmetries of a square. Another remark that I'll make now, and I'll elaborate on this later, is that this particular property of the matrix B here, that its square is equal to minus the identity, allows us to make an important link between matrix multiplication and complex numbers. So complex numbers are things of the form x plus I, y, where I is some kind of mysterious entity whose square is minus 1. But now what we can do is we can connect that x plus I, y complex number with a matrix. We can connect it to the matrix x times I plus y times b, where this I is the identity matrix. Because this matrix B is acting the same way as this abstract number I is. Its square is minus 1 essentially, because the identity is like 1. So this is a way of thinking about the complex numbers represented inside the arithmetic of 2 by 2 matrices. It's another indication of the richness of our arithmetic of 2 by 2 matrices. A few more examples. The matrix 2, 0, 0, 2 acting on xy is 2x, 2y. That's a particularly simple transformation. It just takes a vector and expands it or scales it by a factor of 2. So that vector there is sent to that vector there. This vector there is sent to this vector there. Everything is scaled by a factor of 2. We call that a dilation. We can get more complicated dilations or non-uniform dilations by putting different numbers along the diagonal, but keeping the off-diagonal elements 0. So if we multiply by 2, 0, 0, 1/2, then the effect is to multiply x coordinate by 2, but multiply the y coordinate by 1/2. So we're scaling or stretching things by different factors in different directions. So for example, this vector here, its x component, which is here, gets doubled, but its y component gets halved, so it scales down to there. This vector here, its x component gets doubled, but its y component becomes scaled. So this is a kind of a non-uniform dilation. Here's another example, a little bit more complicated. The matrix 1, 1, 0, 1. This is a kind of triangular or upper triangular matrix. Its effect on xy is to send it to x plus y and y. So the y coordinate stays unchanged, but the x coordinate gets shifted, and the amount that it gets shifted by is y. So a vector like this, for example, its y coordinate is going to stay unchanged, but it's going to get shifted by 1. 1 because its y coordinate is 1. So this vector is going to get sent to this vector. Similarly, this vector is going to get sent to this vector. This vector is going to get sent to this vector. All the vectors lying on this line get moved over by 1 in the positive direction. All the vectors that lie on this line would get moved over by 2. All the vectors on this line would get moved over by 3. The vectors on this line get moved over by minus 1. So this vector gets sent to there, this vector gets sent to there, and so on. This vector gets sent to that vector there. So Everything kind of gets moved. This is called a shear. It's suggesting that it's going to be a little bit perhaps tricky to visualize an arbitrary or more general transformation. So for example, suppose we have the matrix 3 minus 1, 1, 2, which sends the vector xy to the combination 3x minus y and x plus 2y. How are we going to visualize that? Well, the key idea is this transformation is a linear transformation. What is a linear transformation? So suppose we fix a matrix A and we define the corresponding mapping or function that takes a vector x to A times x. And we call that mapping T. So we think of T as a function or map that inputs x and outputs A times x. Then the main fact about this kind of transformation is that it's a linear transformation. And that means that it has these two properties. First of all, that if we multiply x by lambda and then apply t, we get lambda times t of x. So if you scale the input by, say, 3, then the output is also scaled by 3. If you scale the input by minus a half, then the output is scaled by minus a half, and so on. And the second property is that if you apply t to a sum of two vectors, then what you get is the sum of t of x and t of y. Okay? So these two important properties define what we mean by a linear transformation. So I'm going to leave it to you as an exercise, and we'll talk about it later, to convince yourself that when you multiply by a matrix A, that these two properties hold. Okay? It's an exercise. Please write a proof down for that. And why is this important in terms of visualizing the transformation? Because it implies the following relatively simple idea. That suppose we want to apply the transformation T to a combination x e1 plus y e2, where e1, e2 are perhaps our standard basis vectors. Then applying both of these, first of all the second one, this is t of x e1 plus t of y e2. And then applying the first rule, the x and the y, which are just numbers, can come out. So this is x times t of e1 plus y times t of e2. And that's telling us that if we know what the vector t of e1 is and the vector t of e2 is, just those two particular values for t, then we can figure out what t does to any vector. Right? So if you know t of e1 and t of e2, you know t. Next time we're going to apply this linear idea to visualize linear transformations corresponding to 2 by 2 matrices in a slightly different way. We're also going to introduce rotations and talk a little bit about applications of 2 by 2 matrix arithmetic to some geometry. So it's going to be more 2 by 2 matrices next time. As for exercises, well, what I suggest, besides the exercises that I've already given you, simply write down a few 2 by 2 matrices and see what those matrices do when you apply them to column vectors. Visualize, try to get some experience with what happens to column vectors when you multiply them by matrices. So I hope you'll join me for next time. I'm Norman Wahlberger. Thanks for listening.